Hello, welcome back everyone to Planet Geo. Today is June 12th, 2060. It's a monumental day for us. This is reporter Yong Kang reporting live at the Martian bases where they are about to construct the first central hub of Mars. In year 3000, birds became sentient and they established their highly coordinated network called the Tweet Network, super intelligent network. And with that, they're able to greatly innovate and coordinate in the space innovation, surpassing humans and establishing a strong presence on Mars, setting up 3 bases on Mars across the surface for research, military, and residence, respectively. In order to attract more birds to live on Mars, they scoured the site for potential locations for the hub. However, they were unsure of where actually to build the hub, and therefore they consulted Earth's mightiest heroes.
Thank you, Yong Kang. I'm Sean, and before we start looking for a solution, it would be useful to first define some notation to formalize the problem. Specifically, let us see how we can restate what we know into a problem related to graph coloring. We can start by representing the surface of Mars as a sphere denoted by a set S. Then with this set, performing a stereographic projection with an appropriate projection point will project these points on Mars onto a 2D plane. A stereographic projection can be thought of as positioning a point light source on the surface of the sphere. Then for all other points on the sphere, the location of their shadows will be the stereographic projection with respect to their light source. After projecting the surface of Mars onto a plane, we can represent the projections of each of these 3 roads with a parametric curve gamma. Similarly, we can model the bidding behaviors for each of the bases with functions that take in some coordinate on the plane as an input, and then it returns a value that represents the amount that the base would bid for a given location. With these functions, we will also need to consider introducing notation for some of their potential outputs. These would be the coordinates of the base locations and site locations. And we will denote the location of the bases by U0, U1, and U2, and the site locations by V1 to Vn, supposing that n site locations were identified. With these notations, our original problem is then equivalent to finding a point P such that all 3 bases bid the same amount for it. Moving on, we will now construct the associated graph coloring problem. You'll first define a vertex set V that contains all locations of the bases and the sites. The edge set of our graph will be some triangulation of these vertices. We also define a set of 3 colors to represent each of the 3 bases, and then for each vertex, we will assign it a color according to the base that bids the highest amount for that location. But because of the road network, there is a constraint on the bidding patterns Fi. Specifically, for some point P along the road K, the base that is not connected by the road will always bid the least out of the 3 bases. And now that we have formalized the problem into one of graph coloring, it's important to take note of the assumptions that we made along the way. As mentioned earlier, we assume that Mars can be approximated by a sphere because we want the stereographic projection to be a bijection from the Martian surface to the 2D plane. We also assumed that the selection of the appropriate point of projection. Such a point will be one that is not a location of a base or potential site, or points along the road network. This restriction is because there is no bijection for the projection point under stereographic projection. We also assume that the roads do not intersect because there is ambiguity for the base that is not connected to a road at that point. One useful consequence of the assumption is that we would also be able to find a bijection from the road network to a triangular graph. With these definitions out of the way, how do we actually solve the graph coloring problem?
Thank you, Sean. My name is Sheng Xiang, and I'll be covering the next part of our presentation, the link to Sperner's lemma. Starting off with the legend, we'll be defining the research, military, and ice bases preferences for the hub as a yellow, green, and blue circle respectively. Next, for the triangle that you are seeing on the screen right here, this triangle represents the surface of Mars from a top-down view, and this will allow us to find an optimal hub's location using Sperner's lemma. We first define the 3 bases to be situated at the 3 corners of the triangle, as seen here: research, military, and ice. Given that each point in the smaller triangles are possible locations for the hub, At each of these three corners, each base will prefer the hub to be built next to it. Therefore, at the three corners, it will be colored yellow, blue, and green respectively, as shown here. Next, due to the bilateral agreement between the two bases along the edges, the vertices along each edge can only be assigned one of the two colors shown at its endpoints. So for instance, at the bottom, it can either be blue or green. On the left, it can either be yellow or green. And on the right, it can either be blue or yellow. So what about the vertices in the middle? The vertices in the middle will then be assigned colors according to various factors defined in the utility function. So for instance, terrain. So this is a possible set of coloring that can be assigned to the vertices in the middle based on the various factors. So once done, Sperner's coloring can be achieved with at least one triangle with the three corners of all three different colors. Right? In our example, as you can see, we have 5 of such triangles highlighted in red, and all of these triangles are equally suitable for the new hub's location.
Now, given this link to Sperner's lemma, how do we find a suitable hub location within the original context of the problem? We know that if a graph has a Sperner coloring, then there must be a smaller triangle within it, such that each of the vertices of this triangle are assigned different colors. This means that there are 3 adjacent sides, such that each of the 3 bases bids the highest for one of these sides. But this is not what we want. We want to find a single point where all 3 bases bids the same amount for it. To find such a point, we can consider identifying more potential site locations, and this would result in a finer triangulation of the graph, therefore bringing the 3 vertices of the triangle closer to each other. And if we could identify infinite potential sites, then the vertices will converge to a single point. This point would correspond to a suitable location for the hub because all 3 bases would place equal bids, thus solving our problem. However, this is not feasible because when we identify more sites, we will also need to conduct more auctions, and this will take a lot of time. Instead, let's take a step back and realize that the central hub occupies some non-zero area. Then, as long as all 3 points are within the footprint of the hub, we can consider this point to be suitable because all 3 points are the most satisfied for at least one point within the hub. And all this is well and good, but Sperner's lemma only proves the existence of such a triangle within the graph. How would we actually go about finding such a triangle?
Thank you, Sean. My name is Shang Hong, and I'll be presenting on how to use the epsilon approximate algorithm to find a triangle with Sperner's coloring. Firstly, we triangulate our space S to a pre-specified epsilon tolerance. Then for every vertex, we query the utility function of each base and pick the base with highest utility as the label like so. Then, we will use the trapdoor argument to find a triangle that features all 3 colors. Let triangle S contain rooms, which are elementary 2 simplexes. A simplex is a generalization of the notion of a triangle or tetrahedron to arbitrary dimensions. The elementary 2 simplexes are defined as the smallest triangles contained in S. Each room is bounded by 3 edges. Without laws of generality, let a door be defined as an edge with blue-green vertices as endpoints. Now, we have 3 possible coloring configurations of our elementary triangles. What are the possible number of doors for each room? Here, we make a key observation that every room can have either 1 or 2 doors. Rooms with exactly 1 door are the special 3-colored ones. Next, we can start entering the house S by one of the doors at the bottom. The room we are in has either 1 or 2 doors. If we reach a room with only 1 door, we have found our special 3-colored triangle. Otherwise, we step into the next room via the second door, known as the trapdoor. The walk we took through the rooms using trapdoors is known as the trapdoor path. There is also a case where we walk back out through a boundary door of S. That is okay. We observe that we have an odd number of doors, and trapdoor paths only connect an even number of them. Thus, we will find a door with a trapdoor path that leads us to an elementary triangle with Sperner's coloring. Assuming that we pass each door once, and all rooms must have at most 2 doors, no room is ever visited twice. Since the number of rooms is finite, the process must end either by walking into a fully labeled room or walking back out through a boundary door of S. If we found a triangle with Sperner's coloring, choosing any vertex of this simplex yields a location representing the desired epsilon approximate solution. However, triangulation to a pre-specified epsilon tolerance could yield an exponentially large number of elementary triangles. and querying all the vertices can lead to a large computational cost. Since the number of trapdoor paths only cover a small subset of the triangulated space, it is not necessary to query all the vertices of S. Thus, it suffices to only query basis preferences on vertices near a trapdoor path. Combining all the ideas we discussed in the past few slides, we now arrive at the optimized epsilon approximate algorithm. Feel free to pause and take a look at the algorithm.
Thanks, Shang Hong. This is Rui En here. We will see how we may generalize the solution presented. Years after, Nash decided that an underground hub helps to conceal the birds from humans. In their survey, they found an additional base set up by John. Now, there is discussion within Nash to develop a new underground hub that connects the 4 existing sites. Fortunately, the solution and procedure discussed above is extendable to 4 bases in 3 dimensions. We use 3 simplices instead of 2 simplices, and we note that the existing tunnel spaces impose additional constraints on the utility function. For hub sites that lie along each face of the 2 simplex, the base not connected by the tunnel space will be least satisfied. Following, we follow notation covered by Sean. Let I take the value of 0, 1, 2, or 3, and let the color set C take on 4 distinct labels. The definitions for graph G, utility functions f of I, and graph coloring phi stay the same as before. Let S be the 3 simplex with vertices U of I. We triangulate it by barycentric subdivision to obtain arbitrarily smaller meshes and color the vertices as per the utility functions above. Sperner labeling condition is satisfied due to constraints on each f of I from existing tunnel spaces. Thus, we can apply Sperner's lemma. Using the same principles described in the epsilon approximate algorithm, we follow the trapdoor paths. However, instead of 2D rooms, we now step into 3D rooms, and also we traverse faces instead of edges. As Sperner's lemma holds for the n simplex, we can always find a room with Sperner's coloring. Thus, we are always able to find a site that satisfies all 4 bases.